All right, guys, welcome back. So I'm just gonna let everyone in. Okay, so now I think everyone's coming in. We're just gonna, in this second half of the video for today, we're gonna continue with our discussion of TensorFlow, right? And what we were doing. All right, so let's go ahead and continue. So I'm gonna, if you remember, this is the code, okay, that I downloaded from the GitHub. Okay, so we went to our GitHub here. TensorFlow 2, general examples, and we are currently at basics, and we are looking at TF2 examples. You can just download that code, and I'm going to continue the exercise of just. All right. So here we have the terminal, and now I'm going to open up. So I'm going to do ls-l. And we were looking at TF2 examples. So I'm going to open this up in Nano. TF2. All right, I'm going to mute your microphone. Have your microphones on. All right, so let's keep going then. All right, so we had discussed all of this in the previous video. And then in this video, we're going to pick up. So we talked about the function decorators in that previous video. Okay, and we talked about the define input signature, and then basically we printed out these values. So that's where we were. All right, so now we're going to continue in the next segment, next block segment. You can see that here. Okay. I have two things, so I'm going to remove the comment. This comment, comment it out. You can do the same if you're following along. And I'm going to remove this comment over here. Okay, so now we're going to discuss another topic, which is, if you remember in the previous example, I created a constant. So I had A, B, and C. They were tf.constants, as you can see here. But in the new example, in this example that I'm doing now, they're not constants. They are variables. So in TensorFlow 1, there used to be this concept of tf variable. There was also tf get variable, which was confusing. And there was also this idea of placeholders. Three different things with three different purposes. And I like actually the placeholder idea, but here in TensorFlow 2, the focus is on TF variables, basically. And in fact, we're not going to be creating placeholders. So here I just create a variable, but this is really the variable that will change, right? So this is either the data that I'm going to be reading from, let's say that I have MNIST data or Twitter data, tweets, images, all of those are going to be processed and they're going to be stored in a variable, okay? So that's an important concept. Also, the data that you're learning. So remember that everything we do, and I've discussed this a lot in machine learning, right, in the class, but we're creating a type of function like this, right? A weights times x plus b, right? And so all of these are going to be variables. So here, for instance, this x would be this x, right? The data that I read, and then the y is what I'm predicting. But remember, through optimization, which is really what machine learning is, I have to learn the values of w and b. All right, so all of these will have to be tf.variables. If you remember, we initialize them, and you remember I talked to you about how gradient descent is like a giant searching for a treasure in a mountain range. So, you've got to start in multiple places, right, when you're searching for things. And so that means that you initialize the values. You can see here there are many different ways that you can initialize values. In this case, we are just creating the TF variable x, and we're going to initialize it to the values 1, 2, and 3. You can see that it looks like a vector 1, 2, 3. And then also, because this is a node on the TensorFlow graph, we can give it a name. So in this case, var x, okay? Once I create it, notice I can go ahead and do print. I can also do tf.print, right, of x. Okay, so I can try those different things. Notice over here, I also left for you to explore as part, not as part of homework, but just as part of exercise. You know, figure out x assign, what is that? X assign add, what is that? X value, you know, returns the value in a tensor format, right? So I want you to, so what you might want to do is, you know, do that. Okay, so I want you to, you know, play with these things beyond kind of what I'm just giving you here. But we, you know, all these different ways that you can print. If you believe it or not, this, something as simple as this in TensorFlow 1 was not trivial to do, okay? But now we have, that's where, you know, upgrades do work, you know, have a lot of ways of viewing things. Okay, so let's go ahead and do that. And then over here, I'm going to actually, I should have a new line character here, so modify your code, or a break line, because this is actually from this one right here. All right, so let's run this one and just see what happens. So remember, basically I want to visualize X, and I'm trying to 3 different print statements. Because that's the thing. If you, sometimes there are so many ways of doing something. Okay, so run it. All right, and you can see there, I have, this is the new output that just came out. Notice that I print the vector 1, 2, 3. I printed it at 2 different times in 2 different ways. Plus, in one, I actually just printed out the object. The TF variable node object, right? And you can see when I do that, I can see things like, oh, here's the name. It's called var x. And then, oh, over here, here's the shape. Notice that shapes in TensorFlow 2 are tuples, all right? Even if you don't have the second value, you leave it blank, all right? But, you know, that's, I don't know, that's another thing that you just have to get used to. It's got 3 values in there, right? 1, 2, and 3. It's an int32. You can see the value in there. It's just an array 1, 2, 3, and you know, so on. Okay, so that's basically it. So pretty simple, but you know, it's very useful to be able to do that sometimes as you're debugging your code. All right, so you guys will play with this one. Where was I? Here, right? Yeah. So you guys can play with these functions and figure them out. You can always go on Google. You know, TensorFlow has a lot of data, a lot of pages on explanations. Look up the function. It'll give you an example of how to use it. So I do recommend that you take a look at that. All right. Another topic that we're going to cover is subclassing. This one, or classes in general. This is subclassing actually. So I'm not going to run this code because this is going to be part of that other folder, functional API and subclassing. So we'll get to that one. But this is just as a reminder, if you don't remember how to write standard object-oriented classes in Python, go ahead and start reading about that. We'll probably get to it next week, next time we meet. But basically what happens here, just to give you an idea, there is such a thing called the tf.module. And what that means is basically the entire module of TensorFlow. So the importance about this is that inheritance. You can create subclasses that inherit the properties and methods of a bigger class. So for instance here, this is a generic example. You create class, my module. It inherits the TF, the whole TensorFlow module. and then you could do things with it, right? So you have, for instance, here, and we do this is the constructor init. Remember, this is 2 underscores, underscore, underscore, init, underscore, underscore, and then the self. I'm not going to explain what self is because that's just knowing Python and object-oriented programming. Find a good tutorial on it, and you know, make sure you understand it. But here you can see, you know, this is the first time we're going to call Keras. You can see tf.keras. We called initializers, and then we called the famous Glora normal initializer. And when you create that object, then now you can create objects like w1, w2, which are tf.variables, right? So you can see self contains those classes, those objects, w1, w2, which are, in fact, TensorFlow variables. And they are initialized using the Glora initializer. You can see that there. And then we just have to specify the shape. So this is going to be 2 by 3, and this one is 1 by 2. So remember, whenever you see that, right, that's the shape like of an array. You know, 2 rows, 3 columns, or 2 samples, 3 features. And then down here, you would see one feature, or sorry, 1 sample, 2 features, okay? And then once you've created your class, whenever you want to call it, you basically create an instance of that class, right, by doing so my module, okay? So that's basically subclassing. As I said, for now, I'm just sort of introducing this, but we're not going to use it today. It's really just to get you to work on classes. So I'm just going to leave it commented out, okay? And then certainly when we get the functional API, we're going to start using it for sure. All right, any questions about this? All right, seems like there's no questions. Okay, so let's continue then. So here we have, so here I'm going to leave that commented out, but now I'm going to remove this comment. I'm going to remove this one because this I do want to run. Just going to move it down to there. All right. So now we can focus on this little segment here. And you can see basically here, I have another example of function declaration. Okay. Now look at this one. Here I'm going to create a variable outside of the function declaration. So I'm going to call it weight. So remember again, usually we've talked about this quite a bit. We are always trying to build wx plus b, right? Remember though that w is a vector, x is a vector or matrix, and b is a vector, right? So they're not just one value, they're vectors. And again, a vector is, you know, w, you know, a, b, c, these are all values, dot, dot, dot. All right, so we want to basically build this model, right? And so we're going to create, you know, the necessary elements. So we need the weights. So w might be the weights, right? And we're just going to define it to be tf.variable, right? And then after that, we're going to say that this is a like that, right? So tf variable, we need to define 2 things. We need to define for the variable what data will be in it. So in that case, we just say we want data to be a random uniform distribution. So that means it's going to follow a distribution that is uniform distribution, and it's going to pick random values from that distribution, okay? We also need to define the shape, right? So this one is going to be 3 by 3, okay? Later on, we're going to learn that we don't just randomly pick these shapes. The shapes depend on the inputs and the outputs, which basically depend on architecture, okay? But for now, we're kind of just understanding the mechanics, so it doesn't really matter. And so it's just going to be a matrix that has 3 rows and 3 columns, a 3 by 3. Okay, so I've created that. So no longer using constants. Notice here, like in the previous example, and now they're not scalar, but they're matrices. Then we do the same thing over here. I do function declaration at TF function. Notice I didn't use the input signature. And then I define my function. So in this case, I'm going to call it compute C. The value is X, so it's probably this X, right? That X. To simplify things, I'm just going to get rid of the bias, right? So just, for now, I want to just keep it simple. So basically what I'm doing is I'm going to perform a multiplication, and I don't know, usually I would write a dot here for the dot product, but it's just like a weird little dot. So this type of multiplication, it's not going to be an element-wise multiplication, okay? This is going to be a matrix multiplication that I'm going to perform. That's a principle in linear algebra, and we will talk a little bit more about it later, okay? So that, that's just from math. So if you've taken linear algebra, you know exactly what I'm talking about. And so it's a different type of element, it's not element-wise, but it's a different kind of multiplication. We'll do some exercises on that just to kind of explain how that works. But for now, just for the mechanics of it, let's just think about the difference, right? So before we've done element-wise, here we are not doing element-wise. So we're doing, this is a matrix multiplication. And this is actually extremely important. I want you to understand that this is so important that it won't go away, right? So this is the one thing in deep learning. It's the one single operation that really revolutionized machine learning because GPUs do this very efficiently. In fact, GPUs are exceptionally well at performing matrix multiplications. It's literally all they do. And so, or the main thing that they do, this was developed for graphics. As you know, you would have a mesh and you would multiply it times something else, and then you would provide a kind of a displacement, right? You were able to move the mesh from one position to another by just doing a matrix multiplication. What it is it's an operation that can take a matrix and another matrix that have specific and correct dimensions, but they don't have to be the same. And you perform the operation, the dot product, and then you get a new matrix, which will have the data that you want, okay? But intuitively, it's basically like saying that I'm going to multiply W times X, and that gives me Y, okay? That's kind of what we're doing here. That operation, only not element-wise, but matrix multiplication, is the operation that you perform in deep learning, right? And that's what we're doing here. So I create the weights of size 3 by 3, okay? And then I have TF function, okay? And then I have the function declaration. Then I have the function here as we define what a function declaration is. And then all we do is we perform return tf.matmul. And then that gives us, that basically takes weights times X, and it's going to give us a result. Does that make sense, guys? Right, so probably what I will do is I'll do a lecture on this, on the difference between element-wise and matrix multiplication. And then I'm just going to give you a homework assignment with a whole bunch of little problems of matrix multiplication versus element-wise so that you can see the difference. Questions? All right, I do want to stress this is really important, so pay attention to this one, okay? Sometimes it'll happen that you're implementing a complex algorithm that like a transformer. And for some operations, you have to do element-wise multiplications. And for other operations, the main operation when you are doing this, right? The main operation when you're building the inference function, it'll be a matrix multiplication, okay? They produce different results based on, what they are. Linear algebra and everything is a mapping. It's what is called a projection. So you take something and you want to project it to something else. So you do a multiplication of the elements, okay? But, I'll explain that a little bit better, the concept of a dot product later on. All right, so anyway, now that we have this, we can try it out. So I have, over here, I have the variable x. Now I'm going to initialize it to be tf.constant. Notice that it's a vector of little vectors, 1, 2, 3 here, of tf float. And then I'm going to plug in x here and perform compute. You can see that there. I'm going to call my function, and then I just print the result. So let's go ahead and try this out. So I'm going to do Control X, yes, enter. And there you go. You see that the output was not element-wise, right? Do you see that? That's an important distinction. The output is not actually element-wise, okay? So let's take a peek at that a little bit more. So I'm going to scroll down over here. And what I'm going to try is, we have all of these things, right? All of these very interesting things over here. So let's put them to use. This is where those things could come in handy, right? So what I want to do is I'm going to do tf.print or print, right? And I'm going to say, you know what? I want to see, no, the first one was weights, right? So I'm going to see weights dot numpy. I'm going to take a look at that one. All right, so let's try that. Okay, so you can see here, I printed out my data. You see that? Printed out my data. That's the weights that I have in there. Then I'm going to do the other one. I'm going to go back into the code. And I'm going to print out x. So I'm going to go ahead here. This is the same, tf.print. And x is also a tensor. So I'm going to say x.numpy, which basically converts it from a tensor to a numpy. And that just gives me, numpy is a little bit more convenient to visualize. So now I'm going to take a look at that one as well. You can see that there. So now I have this one times these, and that gives me 3 things. So it's basically like I take, let's say here it doesn't matter because I have I got 3 dimensions in that direction and then 3 dimensions in that direction, so it aligns with these 3 directions. So it doesn't really matter how you place them because we're just doing a multiplication. But in other situations, we have to align these perfectly. For instance, let's say that this is just, a vector, a column vector, or a row vector, right? And we, here we had 5 by 3. Then the multiplication will only work if we're multiplying these 3 by the 3. If we were multiplying these 3 by the 5, it would not work. So there it would be kind of a problem. But here it isn't because they're both 3 or 3, so it doesn't matter how we put it, it's aligning with them. So what you can say is that I'm multiplying this whole thing by the first column, and that gives me the first value. Then I'm taking this whole thing, multiplying it by the second column, and it gives me this value. Then I'm taking this whole thing, multiplying it by the third column, and it gives me this value. And there's an actual operation that is being performed and everything. So we'll call the dot product, okay? So we need to talk about that. Now that we've gotten to this, I like to do this. I get to something, see the need for it, and then we talk about it. So now that we've done this, I see the need for us to have that discussion, okay? And so we'll do that at some point a little bit later. But just be aware, if you're curious, you can always look up dot product, and it's very simple, really. I mean, it's just it'll give you a lot of examples of how it works, and then the intuition is that you're projecting a vector to another vector, and so we'll see that as well. But anyway, here we perform the operation, and this is one of the most essential operations. So that's basically like saying that x times weights gives you y. Okay, so that's really what the way that you can think of it. So again, I'll repeat: x matmul w's gives you y. Okay, now if I go back to my code over here, you can see something very interesting. Actually, I keep saying y, but the letter is actually z, right? So the letter, where was I? The letter is actually compute C, right? Intuitively, it says C. Why doesn't it say compute Y? Why does it say compute C?
Because our computational graph is like Z is equal to 2 times A minus B plus C.
You mean in the original equation that we had? Was that what we used?
Yeah.
That's true, but it's the same question actually. Why didn't I say Y here instead of C? So if you go back to the lecture last week, I explained that. It's because this C is sometimes referred to as the logit, and what the idea is that, wait, not here, I shouldn't, that's not, sorry. Here. So the C, if you remember, as I was talking about this last week, the C then goes through a function, remember? Whether an activation function or some other kind of function, but it goes through it. And so that's why intuitively we don't write Y, we write C. So really what's happening here is that you're saying this would be function, right, of that. And so what's inside here, that's why you call it C, to imply, okay, that still needs to go through the function, which makes it into Y. Does that make sense, guys?
Yep, got it.
So that's really why we're calling it C. It's just that, you know, something to remind you of what's happening here. But anyway, so we've talked about this a little bit, right? So we talked about it a little bit. And so now we have a better understanding of it. Okay. Let's keep going then. Are there any questions before I move on to the next topic? No? Okay, so let's keep going then. So the next thing is, so now I'm going to go over here. I'm going to remove this comment, okay, and then I'm just going to scroll down here and remove this comment here. All right, so this is another concept that for right now, I'm just throwing it at you, okay? It's not something that we're really going to be using right away, but eventually, as you even be, so this is even for Keras, you can do a lot of Keras without this, right? Just like function decoration, you can do a lot of, you'll see a lot of the Keras that we do. We're not even going to be using it per se, but these are concepts that as you start to advance into the low-level API of TensorFlow 2, you have these functionalities. So as I said, I'm kind of introducing these ideas so that you're sort of aware of them, in the hope that by repeating them, they'll help you. So here in this function, so we're done with this previous one that actually is really important. I would stress, practice it a lot. Here we're talking about a new concept called the, for lack of a better term, I guess, the gradient tape. Okay, and you can see the name is over here. So this is another one of those quirky things that TensorFlow 2 introduces. It's an advanced concept, again, that wasn't there really in TensorFlow 1. And the idea was this: you have a computational graph, right, that you're training. As you guys know, you do training and testing. So you're training your graph. And it's just so happened that in TensorFlow 1, it was really difficult to view the values as you're training, to have a lot of control, customization, all of that. TensorFlow 2 has addressed that by creating something called the gradient tape. So the gradient tape is this idea. It's almost like a tape, you know, like the idea of a tape. Imagine there's like, so what's happening is you have an architecture made up of many hidden layers. And between every layer, there's weights that you're learning. So using what is called the back propagation algorithm, forward propagation, back propagation. So basically what that means is you start with X propagates forward to the classes, you predict the value, you measure the performance of the algorithm given the predicted versus the actual, and with that feedback, you work your way back to modify the weights, right? To, you know, if it was good, you modify the weights in this way. If it was bad result, you modify the weights in another way. So that's really the idea. That's how, you know, gradient descent works. Through that algorithm, you achieve that. But the gradient tape is really about recording, having a way to record the values in your algorithm that are, you know, that are being learned. Okay, so it's something that they have introduced, and so that's why it says it's for automatic differentiation and for computing the gradients, right? So the idea is that it's a mechanism that allows you to record that. As I said, you know, it's not something that you will need necessarily right away, but it's something that for people that are really customizing their algorithms, they're not just using like the standard plain vanilla algorithms, right? You know, then they can use this for debugging purposes. The way it works is you can see here, you have, again, the same idea, right? So same idea. We have y equals wx plus b, right? So we are trying to learn those parameters. We have batches of thousands of records that we give as x and y because it's supervised learning. And then we give it one batch, it predicts, we compare that to the real. Based on that, we work our way back and modify the w's and the biases. Great, then we do another batch of x and y, predict, compare the results to the real, and then work our way back to the w's and the bias. And you do that, and there's a lot involved in that. And so here we have the algorithm and the example. You have w. Again, just here we're not using just scalars, just one number. So we have tf variable 1, it's w. The bias is 0.5, right? We just initialize into something for this example. And then we have some data over here where we actually just give it a scalar 1.4, 2.1. We use the built-in function convert to tensor. TensorFlow has this. And now we have values for x and y. You see that there? Then after that, this is how you invoke the gradient tape. You do with tf.gradient tape as tape. Okay, and that means that you created an object called tape, and then that object is basically a gradient tape. And then here, usually what you put is this, right? So you take the same the z, which z is this one, right? So z, because y is really function, the activation function or whatever of z, okay? And so we do the same thing here. Now notice that instead of writing the equation like this, right, now we are changing it, right? We're also not going to do the mat mul as we did over here, TF mat mul. You see that? Here I used, or it is used, TF multiply, which is element-wise. But the thing is, it doesn't matter here because these are just single values, 1.5. They're not vectors or matrices. So then you don't have to be worried about, you know, element-wise or things matching up. And so you can just do a multiplication. Okay, so that's really just a simplification. But notice that this operation takes TF dot multiply W times X. The result of that is added to B by doing TF dot add. So we take the result of this and B, and we do a TF dot add, and that gives us Z. Now, the important thing here is that we didn't do this outside, right? Like we had done here, where we just had it in a function somewhere, or we can have it outside. Here, we're doing this inside TF gradient tape as tape. Okay, so what this shows is, in a sense, it's a way of wrapping your code. So you could have done it without the TF gradient, right? But the advantage of doing these two, this one and the next line within, is that now you can reference them through the object tape in the computational graph, which you couldn't do before, okay? So that's really all it is. So through this, they are now in the tape, and this tape can be referenced from the outside. So you can see that the C is done here, right? And that predicts a value. And then that value, it's not running through a function, but instead we're just comparing Z to the actual. This would be the real. So this would be, you know, in Y test, you know, the Y test values that we learned from sklearn. So whereas this one, you know, just to simplify it, I'm going to make up a function here, but remove it later. And I'm just going to say ypred equal function Z, okay? And so now this C over here would be ypred. You see that? And so that's what's happening there, is that now you're going to take the predicted value and you compare it to the real. So if it feels better for you, I can just call this real, okay? But just make sure then over here, you call this one real. Okay? So you're comparing those two values, and then what's going to happen here is that you have a basic least squared errors, which is something, you know, like when you learn linear regression, right? LSC, the sum of the squared errors. Okay, so here you take these two vectors, take the difference between them. Because they could be negative or positive and you just want the difference, you do square. When you square something, it gets rid of the negative, right? So now you have that value, and then reduce sum here. If you had a vector, it's just going to take the sum of it all, because that's the sum of squared errors. So if you remember, LSC is the sum of errors, right? Of errors, squared errors. So squared errors, and this is, you know, like you saw before, y real minus ypred. Okay. So again, you know, a lot of these things, certainly in 530, we're going to spend a lot more time on the theory behind the scenes. Here, I kind of want you to understand the mechanics a little bit more, but I'm throwing in these ideas as reference. You can always look this up, least squared errors. And that's basically what is happening here. Right, so that means that you have now in the computational graph the nodes as we had before for the multiplication, a new node which takes the function C and gets you ypred, and then now you have the loss, another node that compares the differences, okay? So I just made the computational graph a lot more complicated. So what I'm gonna do is, I'm gonna get rid of this function just because it's not, I haven't defined it, so it's not gonna run. But let me switch over to the whiteboard for a second. Okay, so I'm gonna switch over to the whiteboard. And I'm gonna take now that enhanced example and represent it as the computational graph. So if you remember, we have what? We have Z, that's a node. So we have Z, that's our node. And then that we are saying that we want it to be plus B. And here we have X and W. And this is a matmul operation. Like that, right? That's the computational graph as we have it so far. But then C goes through a function. C goes through a function, and that's a node, and then that node becomes Y, right? So that's the computational graph so far, right? This part over here. Right, and then here I just got rid of the function because I haven't defined activation functions yet, so I don't want to, my code will not run, but you know, that's kind of what I'm doing. And then this Y pred now becomes this value over here. And now I'm going to use another equation called the least squared errors function, which is the one that when you took your linear regression class, you should have discussed this. And that function just says that we want to, we have a new function where we want to minimize the sum of errors. All right, so let's think a little bit about that. So what does that mean? It means the following. Every time you give it some data, you have Y and you have Y pred, let's say this is Y pred and this is Y real. Or actually, let me, so it's more. So this is Y pred. Which stands for predicted, Y pred. All right, and then over here I have Y pred and Y real. Okay, a little table. So I have, let's say in Y real, I knew the values, right? And then I have X. So for X, you know, 5, 2, 0. Y real was 1, 1, minus 1. Y pred predicts what? Predicts 1, minus 1, minus 1. You see there's one error here, right? A more intuitive way of understanding this is from linear regression. We're just going to say 5, 3, 7, and then this, those are the real numbers, and then this one predicts 5, it predicts 2, and it predicts 7. So what's going to happen now in that LSC function is that you take the difference between Y pred and Y real. So you take the difference, Y pred minus Y real, and you square it, okay? Why do you do that? Because 5 minus 5, right? That's 0. That's good. So I'm going to do that LSC here. So the difference between those is 0. This one is 0, but this one is 2 minus 3 because it's 2 minus 3. That is minus 1. So the difference between the, now if they were inverted, it would have been what? 3 minus 2, which would have been a plus 1. So when you square these, it doesn't matter how you put them in there, right? It's always going to be positive. So, and actually because the difference is, this should be, let's say 1. So now let's look at it. Right, so if I do, the difference is now 2, right? So if I do 1 minus 3, that's minus 2, right? If I invert them, three minus 1 is 2, but positive, right? But by squaring them, what do I get? In one I had minus 2, and the other one I had 2, right? If I square them, what do I have? In both cases, I have 4. Do you see that? And that's really what you want. So that's the first thing, right? And that's what's happening when you take the difference. If I go back to the code, you can see I'm just doing that. I'm taking them all and squaring them, okay? Now, another thing that's happening here is that this applies, because everything is a tensor in TensorFlow. That could be an actual value or a tensor, right? So what that means is that, you know, I could have, let's say that all of these have differences, right? So let's say that all of these have differences. So this is going to be 3, and this is going to be 6. All right, so then I'm going to end up with 2, 2, and 1. And then when I square them, regardless of symbol, it's going to be 4, 4, and 1. You see, that's what this gives me. Squaring them, so, you know, y hat minus y squared gives me these values for the whole data set, not just for one. I end up with that vector. Is I want to take the sum of them, and I want to pick the set of values that gives me the more optimal one. So if I add all of these, that gives me a 9. Okay, so if I go back to my code over here, you can see that the next step that I do is I do TF reduce sum. You see that of whatever this was. So whatever this was, now I'm going to apply reduce, and this really should say reduce and sum. All right, so what that does is basically now I go into the white space here, the whiteboard, and what I'm going to do is I'm just going to sum all of them, and that gave me a 9. You see that? But I could have, so let's save this value. So I'm going to erase all of that. I'm going to erase these. Right, and that gave me a 9. I'm going to erase that part. Let's say that now I have a new set of predictions, because remember that the predictions y are dependent on what values you learn for these, right? So I learned W and B, one set of weights, right? And remember that y real is, y pred is technically y pred function z, right? Where C is what? C is W dot product X plus B. For all these are vectors, but I learned this set of W's and B's, and it gave me these values, 3, 1, and 6. So let's call this, let's say Y pred given W1, B1, right? Some set. Now I'm going to try another one. And I'm going to say, now this is going to be my Y pred, but with another set, W2, B2. Okay? So that's another set of weights. And so now I'm going to predict another set of values. And this set of values is going to be 1 minus 7, no, plus 7, just 7. And then this one's going to be, I'm just going to exaggerate the number, so 14. So now I take the difference of those, right, and square them, and those are going to be what? Remember, the sign doesn't matter because I'm going to square them, so the difference here is 4. So 4 square. The difference here is 4 square, and the difference here is 7 square. So then I'm gonna, this is 16, 16, what is that one? That's a really large number. 49, right? I add these, and what's the value? 16 plus 16 plus 49. That's 81.
82.
Huh?
81.
81.
81.
Right. So you've got on one side, you've got 81 for weights 2 and W2 and B2, or you got 9 for weights W1 and B1. So LSC says that you want to minimize the sum of squared errors. So if we go back here, these operations are doing the calculations for you, right? So this takes differences and squares them, then this takes the sum of them. And that's your loss function. And then the optimization would try to minimize the sum, right? So given that logic that I just described, if the answer is that the best set of values is the one that gives you the lowest sum between 16, 16, 49, or 4, 4, 1. One gives you 9, one gives you 81. Which set of parameters would give you the better function? The parameter W2, B2, or the parameters W1, B1? Which set of parameters gives you the best equation? The goal
Is
of
it the W2B2?
no, not W2B2. W2B2 81 is higher, right? You want to minimize the sum of squared errors,
Right, got it. My bad.
right? So the opposite, correct? If you want basically the minimum of the sum of the squared errors. Which one of these two is the minimum?
W1B1.
W1B1, right? Because it gives you a sum of errors of 9 versus this one, which gives you a sum of errors of 81. So obviously this is the good set. Do you see that? And that's how you do this process. So really what's happening here then is now I'm going to erase, go back to the, now that I've explained that, let's go back to the computational graph. So as you start building the computational graph, okay, as we start building it, we have ypred, we also have yreal, right, which is the data that we read, the labels. Okay, and what do we want to do? The first thing we want to do is we need to take the difference between them. Remember, these are going to be vectors, so or tensors. So therefore, we just need to apply that. Then we're going to apply to that resulting vector the square operation. Do you see that? And that gives us yet another tensor. And then from there, we apply what? The sum. Reduce sum, right? That function reduce sum. And that one is usually called loss. So whenever we call the node loss, we are doing all of this. And look at how everything is linked together. Do you see that, guys? And that's the computational graph for what I'm doing right now. So if I go over here back to the code, what do I have? I have z, or that function, right? Which is, you know, this part over here, right? That's that. Then I go over here, the function, that's just that other part. And then notice now I have a node called loss. And loss references tf.reduce sum, which references tf square, which references y real and y pred, right? And that's just the formula known as the least squared errors, right? And so this loss node links everything together because y real is up here, right? And then y pred is really this function, which is just z, which is this function over here. So that's how you write code in TensorFlow, and that code translates into a computational graph. So really, whenever we want to perform the optimization, all we have to do is run the loss node. So if I go over here, right, all I have to do whenever I want to perform the optimization is I'm going to imagine just grab that node loss. You should be seeing the whiteboard right now. I grab loss, and loss will make sure that there's data here. We'll make sure there's data there. It'll make sure that it, you know, trains W and B, and then these are all the operations that it needs to do. And that's why it's called a computational graph. Does this make sense, guys? This is an extremely important thing, and that's why I wanted to introduce the gradient tape right now, because once we do this in Keras, it's not always obvious what's going on in Keras. Keras will abstract a lot of this, and that's why I was saying, you know, you can use Keras and TensorFlow and not really get this, but it's going to be much better to your understanding if you do understand this. Are there any questions about the graph and how it relates to this code in particular here? No questions, huh? So what I would say is the analogy is that given that these three lines create the code, create the graph, then think of the gradient tape as literally a piece of tape, and you just took that computational graph and you stuck it to it in a way, right? And so that then what you can do is the computational graph can be accessed via the tape object. So if you can see here in the code, tape is that same tape over here, this one. And now I can access it. So the tape object then can say tape.gradient, and gradient just means the gradient descent, right? So I can run that. And what do I run? I actually run the loss node over here, loss node, and also I run the W node, the weights. Okay, so I can run individual nodes, etc. But basically the most important one is I run this loss one, right? And then that just means that now I can have my results for loss in, you know, whatever. So that 9 and 81 that I had, right? So that's basically what's happening now. If I go back to the white space over here. So if you remember, I had that sum of 81 versus 9, those values, right? Those are the values that I can now return to see what the loss actually was. This is not going to be 9 or 81. It's going to be different, but because the data is normalized, but that's the intuition anyway. And so here then, I called, you know, I create another node, DL loss DW, and then that gives me tape gradient loss, and then I can just go ahead and print the value and so on. Do you see that, guys?
Yes.
Yes? Okay, good. So let's just run this for, I know I modified it. Hopefully it won't break, but let's see. Okay, so there's an error there. Yeah, it's function. I thought I got rid of that. Let's see. Where is the error? Oh, no. Let's see. Oh, it's here, right? I did this just to illustrate something before. All right, I'm going to get rid of this because it's not. I was just explaining things. All right, so got rid of that. And then down here, yeah, I just comment this out, just to kind of show you. But here I'm just making it an equality here, and then y pred y. So that should work. All right, so let's try it. And there you go. The loss is just like we had 81 or 9 or whatever, just some value. And you can see that there. So we have our differences here. Now, and that's it. So that's, that's basically an example. I think it should be useful. As I said, right now, when you guys do Keras, you really will not necessarily have to implement the gradient tape or function decoration, but it's good to understand this, and I wanted to relate this to the computational graph, okay? But Keras does abstract this quite a bit. And then, so really, you take the inference function, the loss function, paint them or tape them, I guess, in the tape. Then you can invoke the gradient and call the node loss W, whatever you want. And then here you get a value, which is a result of the loss. We usually print the loss. So you'll see later on that whenever Keras runs, it'll say loss. You'll see these loss, loss, loss all the time. And you're going to ask yourself, where is that coming from? Well, just always come back to this code. That's where it's coming from. It's calculating a value based on these differences, right? Which I explained by creating this sophisticated graph here. Okay, so that's really the idea. I hope you understand the intuition. I can only ask questions to see, do you have any questions? Or I can only ask you guys, do you have any questions on this? Does that make sense? If we do a pop quiz right now about this, would you get an A?
Probably.
Probably? All right, good. All right, good. So there we go then. So that's the idea. So you create the inference function, the loss function, called the gradient descent algorithm, basically. Invoke that node from the computational loss. And that's going to give you the loss value. You just print it. And just thing to keep in mind is that a lot of the time when we're doing everything in Keras, the code in the background looks something like this, but it's pretty abstracted, to be honest. And so that loss is really this loss. Anyway, so moving on, other things in Keras that you can sometimes define is the optimizer. So for instance, you can say, I want to use a specific type of optimizer, not just standard gradient descent. Sometimes I may want to use atom optimizer or something like that. So if you want to change that parameter, you just do tf.keras.optimizers SGD. So this one stands for stochastic gradient descent. It's a type of algorithm, but it could also be the atom optimizer. So I think atom is just atom like that, might be lowercase. But that's just an example. We're not going to use this right now. As I said, with this lecture, I'm just kind of throwing things at you. And then you can then say optimizer. Once you've declared it, you use it similar to what you did over here, and you do apply gradients, and then you give it DL laws and W and so on. Okay? And then you can print out the W. So it's the same idea. I'm just going to leave this commented out, but I wanted to introduce this as well. Maybe put that in your cheat sheet as something else to look at. All right. Finally, after all that work, we finally made it to Keras. Right? So now that we've actually discussed a lot of very important things in the background. And now what we're going to do is we're going to start getting into the Keras algorithm itself, or sorry, not algorithm, the object Keras. It's an encapsulation of Tensorflow 2 in this case. So here, I'm going to just move the comments out. So this is a new thing, a standalone thing, right? And so let's look at some of the basics. So the first thing we want to do is how do you Keras? So how do you Keras, right? So Keras is, again, like now the tool for machine learning. So just like, you know, I taught you Weka and you did some machine learning in Weka, and then I taught you sklearn and you did some sklearn, machine learning and sklearn. Now I'm introducing Keras, and you will use it to do machine learning. The difference now, though, is that Keras has all the power of TensorFlow. So really big data. So now, finally, now you can do big data with your GPUs in Scholar. Right? So now you can do that. And so again, just like with everything else, Keras has many ways of doing the same thing. So there's a lot of approaches, okay? And this now gets into another issue, which is architecture. Now, we talked about architecture last week, right? We talked about, so last week, do you guys, I don't really want to repeat all of that, but this is where I will say, go back to, at this point, go back to the video from last week where I discussed linear regression, logistic regression, neural nets, and deep neural nets, okay? So, you know, I'll write it even, look at that video. Study last week's video, right? Where I discussed linear regression, logistic, so let's say linear regression, logistic regression, neural networks, deep neural networks. So I gave you all the intuition back last week about the inference function, the loss function, and in particular I said they all kind of have the same function, but with modifications. And for linear regression, you use the least squared errors loss function, which is the one we just discussed, right? This one. But for the other ones, for logistic regression, neural nets, and deep neural nets, we use a different one from LSE called a cross entropy, right? So definitely, I haven't covered cross entropy at all. For now, intuitively, just think of cross entropy as similar to LSE, but you know, specific to this kind of problem. Getting into it would take some time, and so that's actually something I will cover in a lot of detail in 5:30. All right, so cross entropy is the name instead of LSE. So imagine like a little block. We're going to plug, remove LSE, and instead change it to cross entropy. But it's still, it takes the same thing. What's important is that this LSE took, what did LSE take? It took Y pred and Y real, right? For linear regression. And guess what? Logistic regression, neural nets, deep neural nets, Same thing. They use cross entropy, but cross entropy still, regardless of what the function looks like inside, takes y pred, y real. So that's what's really important here. Okay, so as we start, so definitely check out those videos. I know I talked about architecture and I showed you how logistic regression has no hidden layers. Neural nets have one hidden layer. Deep neural nets have 2 or more hidden layers, right? So go back to that video. All right, so anyway, that's kind of what we're doing now with Keras, right? So Keras here will allow us to create a neural network, okay? So this neural network is actually a, this is gonna be, it's a neural net, all right? So we have how many? We have, first of all, it's object oriented, right? So that's the thing that I want you to remember. It's highly oriented. So I create a model, you can give it any name that you want. And then you create the tf.keras sequential. So this is the keyword, sequential. And then now it means that you're going to start to create an architecture. So what you can do, and this is, again, just one way of doing it, model.add, and what do you add? You're going to add a whole layer. So from tf.keras layers.dense, dense just means that it's a fully connected layer. That is that all the neurons from one layer are connected to all the neurons of the next layer. And so you say this layer should have 16 neurons, and the activation function should be ReLU, which is, we talked about that function. Well, I have another code for this, so I'll talk about that later, but just remember it is like when you have, I've said this many times, right? You got C, and then to get Y, you run it through a function. So in this case, ReLU, okay? And we'll explore that in a lot. I have some graphs and everything. It'll look very pretty. All right, so we'll take a look at that later on. But in Keras, you really just do something as simple as this. tf.keras dense, number of neurons is 16, activation is ReLU. Then the next layer means that model.add tf.keras layer dense, and now you have 32, and it's ReLU. And then you have model build, right? And now you've defined the layers, and then you specify the input. And the input can be defined first or last. I mean, there's a lot of ways. But basically, the input just means that this is the X. So none just means that you can have however many samples you want, 100 samples, 70,000 samples, doesn't matter, because none just means any. But you have 4 inputs. So this is iris. So this, for instance, would be iris. Right, iris had 4 features, X1, X2, X3, and X4. All right, so let's run this code and see what happens. All right, so I'm going to run it over here. Boom. So I created a model. It starts over here, right? And it just says model sequential. I have this, right? So I have these layers. And then I have the shapes, of them, however many, and then it calculates the number of parameters. So imagine this tells you how many different weights and variables you have to calculate for that model, okay? And that's going to make it more complicated. And that's why you need a GPU, because as that number starts to explode, you just have a bigger challenge. So just really quickly, guys, bear with me. I just want to finish this. I'm going to do here, I'm going to add another layer, right? I'm just going to say model.add, and then I'm going to say tf.keras.layers.dense, and this last one will be the output. So it could be 2 or 1. So this is not very strict in Keras, and I can do units equal 1. So there's only 1 neuron. And then the activation will be a sigmoid. For instance, sigmoid, okay? And so, oops. All right, and so now I'm going to run this. So remember, it's 4 inputs, then there's layers of 16, 32, and a final one of 1, okay? So I'm gonna run this. Oops. Oh. What's the problem? This is what happens when you are rushing. Okay. You guys see an error here? Oh, I'm missing this, right? Okay. There you go. So you can see now the architecture has become bigger, right? I have now dense 1, dense 2, so I have more layers basically. Okay, now the key question is, you might not get a sense from looking at this or from looking at the code, but really, if you look at it as the architecture. Now, in the computational graph, this is the last thing, by the way. We'll be done in a second. What I'm doing now is I have multiple layers, right? So what I'm saying is it's no longer X here. X still exists, but it's down here, right? And now it needs to go through, I'm just gonna, all of this stuff here, right? All of this matmul and everything, I'm just gonna call it function 1. And that becomes now, or actually I can just call it hidden 1. And that becomes the input to this, right? So it's no longer X, it's X through the entire architecture. Okay, the entire architecture. So what does that look like in the architecture that I created? So if you remember, inputs were 4, right? Inputs were 4. The output was 1, and then in between I had 2. One had how many neurons? This one had 16, this one had 32. So that's the network that I created. These are the inputs. This is the output, right? And then here I have hidden 1, hidden 2. And that's basically the architecture that I created, okay? Which if you want to think of it in terms of the computational graph, it's this, right? So the X, whereas before the X was here, right? It's not there anymore. It is here because it has to go through the entire architecture to arrive at the final one. So really all of this, all of this is architecture, right? Until the final Y pred. And so that is represented as that. Do you see that, guys? This is another way of representing the neural net. That's why they're called neural networks, right? That's the thing that we're creating. I know we're out of time, so I'll basically start here, I guess, next week, but I just wanted to kind of close with that. That's the architecture that I created. So I created in Keras, I was able to create the object sequential, and then I add the first layer, which is 16 neurons. Then the next one had 32. The last one has 1, and it has a different activation function, sigmoid. And then I specify the input, which will be none for the number of samples, and the layers will be 4, basically. All right, I guess we're going to stop here for today. We are definitely out of time. I hope this made sense. I will try. I think it's actually a really good stopping point. Next Tuesday, I will, or Monday, sorry, I will pick up here with the same idea and then just keep going through Keras. And no homework on this. Just practice what we've discussed today. You also have an extension of your Twitter exam. It'll be due a week from today. Okay. All right. So we'll stop here for today, and I will see you guys a week from today. Thank you.
Hey, Professor Calix.
Yes, sir.
So I am filling out some. This is a random topic.
Let me
I'm
just
filling.
pause the recording. Let me pause the
Okay.
recording.